If we look at the VI relationship of a capacitor again, let us start with this relationship again. I is equal to C dV by dt. Once again, remember that this I is a function of time and this V is a function of time as well. If Vt is 0, we get I, if Vt is 0 and is not changing, it remains 0, then I is 0. But if Vt is some value and not changing, I will still be 0. But if Vt is 0, but it is 0 because it is changing, It may not be 0. It's very important. We are going to look at this later on. But let us now derive the expression for how voltage relates to current. So we know that we can write this mathematically as It dt is equal to, or 1 over C, this thing, equal to dVt. So if we integrate both sides, and here the integration is with respect to time, but here the integration is with respect to the voltage at that time. So here the integration is with respect to time, here the integration is with respect to voltage. So here, if we integrate this between two time intervals, so t naught and the present time t, then here the limits would be from v at t naught, the same time, and v at t. And because there is t in the limits, so we have to change this to some other variable. So because here we have v in the limits, we are going to change this v to something else as well. So if we can now solve this, we have actually 1 dx. So this is an integration in x, maybe in x, for example, where x is equal to vt, then we have, this is the integral of 1. So what is the integral of 1? X. So we are going to get v dash t here, and the limits vt naught and vt are going to be applied here. And what are we going to get? 1 over c is a constant, we get it outside, and we are going to get t naught to t I t dash dt dash. Obviously we don't know this expression, so we cannot solve this like this. So what we get here is, when we put this limit, we get vt minus vt naught. So the voltage at this time instant t minus the voltage at that earlier time instance t naught is equal to this thing. Or in other way, we can say that the voltage at a certain instant t is equal to, and this can be taken to the other side and it becomes positive. This is equal to the voltage at some earlier time interval t naught, and then this integral that starts from this time and goes and to this current time t this way. So this is how voltage is related to current. So whenever I is equal to c dv by dt, or there is an expression that involves the derivative, the reverse expression involves the integral. And this term is very important. We must know what happens at this earlier time. So if we say this earlier time is actually minus infinity, the earliest time possible, and let us assume that the voltage on a capacitor at that earliest time is 0. So this expression becomes the V at this current time that we are interested in is equal to 1 over C and integral from minus infinity to t I t dash dt dash. So there's another expression that we should remember. And one other very important expression. So remember this from the older lesson, that when I is defined as the rate of change of charge flowing through a cross section, we have this expression, and Q is equal to the integral from minus infinity to t of I t dash dt dash. We have studied this earlier on. So this thing is exactly that q. So we can write Vt is equal to 1 over C q at t. So the current flowing from since the earliest time to this present time basically makes up the total charge that has been flown through a certain cross section in the wire, for example, or here in this case, the total charge that has accumulated on one plate. And therefore, we can say that the Q, the charge on one plate of the capacitor, is equal to C into the voltage across the capacitor. And this is a very useful expression to be kept in mind. So let us say this is the equation 1 of the capacitors, this is the equation 2 of the capacitors, this is equation 3 of the capacitors, this is the equation 4 of the capacitors. So we have a relationship between I and V, two forms, and then there is a relationship between Q and V as well. Remember, Q is the charge on one plate of the capacitor, and V is the voltage across the capacitor, and C is the capacitance in farad. Q has units C and V has units volts. So this is a good expression to know as well.